All right. I had to take yesterday off because my voice was cracking a lot and I wasn't able to read for more than a sentence before losing my voice. So, yesterday I decided to do a bunch of stuff with the chat GPT. I think I talked about that a little bit in the last video I updated. Just sort of an update of everything I'm doing. I decided I'm not going to cancel out any of the OpenStax books. I should commit and complete all of them. So I'm going to go ahead and do Anatomy and Physiology, Chapter 2, and Anthropology, Chapter 2 today. And then let's go ahead and maybe get the next 3 rolling. Nope. 9, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. Economics. So economics will be yellow. Nope. 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 4. So like psychology will be even after. So I'll do orange, and then I'll do red. Actually, I think that was 8, 10, 12. So I'm just going to go ahead and do so this will be 1, 2, 3, 4, 5, 8, 6, 7. Okay. Oh, I landed on 8. Okay. Oh, and then I'll add that one too. 7 and then 8. So 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay. 8. Okay. All right. And then this, I did that one already. Oh, sorry. Oops. This one I can go ahead and switch. Where's up? All right. Anatomy, physiology. Science. There. Download. File. Beer. Beer. So tomorrow I have to account for one of the bills coming up. So I'll call it $100. So tomorrow I really need to try to make $300. So that's going to be my goal for tomorrow. Chapter 2, the chemical level of organization. Chapter objectives. After studying this chapter, you will be able to describe the fundamental composition of matter, Identify the three subatomic particles. Identify the four most abundant elements in the body. Explain the relationship between an atom's number of electrons and its relative stability. Distinguish ionic bonds, covalent bonds, and hydrogen bonds. Explain how energy is invested, stored, and released via chemical reactions, particularly those reactions that are critical to life. Explain the importance of the inorganic compounds that contribute to life, such as water, salts, acids, and bases. Compare and contrast the four important classes of organic carbon-based compounds: proteins, carbohydrates, lipids, and nucleic acids, according to their composition and functional importance to human life. Introduction. The smallest, most fundamental material components of the human body are basic chemical elements. In fact, chemicals called nucleotide bases are the foundation of the genetic code with the construction or instructions on how to build and maintain the human body from conception through old age. There are about 3 billion of these base pairs in human DNA. Human chemistry includes organic molecules and biomolecules. Human chemistry also includes elements. In fact, life cannot exist without many of the elements that are part of the earth. All of the elements that contribute. Hold on one sec. Oh. Sorry. To chemical reactions, to the transformation of energy into electrical activity and muscle contraction. Elements that include phosphorus, carbon, sodium, and calcium, to name a few, originated in stars. These elements, in turn, can form both the inorganic and organic chemical compounds important to life, including, for example, water, glucose, and proteins. I'm going to quiet down just a little bit, so I'm going to move this a little closer to me. There we go. This chapter begins by examining elements and how the structures of atoms, the basic units of matter, determine the characteristics of elements by the number of protons, neutrons, and electrons in the atom. The chapter then builds the framework of life from there. 2.1 Elements and atoms, the building blocks of matter. Learning objectives. By the end of this section, you will be able to discuss the relationships between matter, mass, elements, compounds, atoms, and subatomic particles. Distinguish between atomic number and mass number. Identify the key distinction between isotopes of the same element. Explain how electrons occupy electron shells and their contribution to an atom's relative stability. The substance of the universe, from a grain of sand to a star, is called matter. Scientists define matter as anything that occupies space and has mass. An object's mass and its weight are related concepts, but not quite the same. An object's mass is the amount of matter contained in the object, and the object's mass is the same whether that object is on Earth or in the zero-gravity environment of outer space. An object's weight, on the other hand, is its mass as affected by the pull of gravity. Where gravity strongly pulls on an object's mass, its weight is greater than it is where gravity is less strong. An object of a certain mass weighs less on the moon, for example, than it does on Earth, because the gravity of the moon is less than that of Earth. In other words, weight is variable and influenced by gravity. A piece of cheese that weighs a pound on Earth weighs only a few ounces on the moon. Elements and compounds. All matter in the natural world is composed of one or more of the 92 fundamental substances called elements. An element is a pure substance that is distinguished from all other matter by the fact that it cannot be created or broken down by ordinary chemical means. While your body can assemble many of the chemical compounds needed for life from their constituent elements, it cannot make elements. They must come from the environment. A familiar example of an element that you must take is calcium. Calcium is essential to the human body. It is absorbed and used for a number of processes, including strengthening bones. When you consume dairy products, your digestive system breaks down the food into components small enough to cross into the bloodstream. Among these is calcium, which, because it is an element, cannot be broken down further. The element calcium in cheese, therefore, is the same as the calcium that forms your bones. Some other elements you might be familiar with are oxygen, sodium, and iron. The elements in the human body are shown in Figure 2.2, beginning with the most abundant: oxygen, carbon, hydrogen, nitrogen. Each element's name can be replaced by a one or two letter symbol. You will become familiar with some of these during this course. All the elements in your body are derived from the foods you eat and the air you breathe. In nature, elements rarely occur alone. Instead, they combine to form compounds. A compound is a substance composed of two or more elements joined by chemical bonds. For example, the compound glucose is an important body fuel. It is always composed of the same three elements: carbon, hydrogen, and oxygen. Moreover, the elements that make up any given compound always occur in the same relative amounts. In glucose, there are always 6 carbon, 6 oxygen units for every 12 hydrogen units. But what exactly are these units of elements? Atoms and subatomic particles. An atom is the smallest quantity of an element that retains the unique properties of that element. In other words, an atom of hydrogen is a unit of hydrogen, the smallest amount of hydrogen that can exist. As you might guess, atoms are almost unfathomably small. The period at the end of the sentence is millions of atoms wide. Atomic structure and energy. Atoms are made up of even smaller subatomic particles, 3 types of which are important: the proton, neutron, and electron. The number of positively charged protons and non-charged neutrons give mass to the atom, and the number of protons determines the element. The number of negatively charged electrons that spin around the nucleus close to the speed of light equals the number of protons. An electron has about 1/2000th the mass of a proton or neutron. Figure 2.3 shows 2 models that can help you imagine the structure of an atom. In this case, helium. In the planetary model, helium's 2 electrons are shown circling the nucleus in a fixed orbit, depicted as a ring. Although this model is helpful in visualizing atomic structure, in reality, electrons do not travel in fixed orbits, but whiz around the nucleus erratically in a so-called electron cloud. An atom's protons and electrons carry electrical charges. Protons with their positive charge are designated P+, electrons have a negative charge, are designated E-, an atom's neutrons have no charge, they are electrically neutral. Just as a magnet sticks to a steel refrigerator because their opposite charges attract, the positively charged protons attract the negatively charged electrons. This mutual attraction gives the atom some structural stability. The attraction by the positively charged nucleus helps keep electrons from straying far. The number of protons and electrons within a neutral atom are equal, thus the atom's overall charge is balanced. Atomic number and mass number. An atom of carbon is unique to carbon, but a proton of carbon is not. One proton is the same as another, whether it is found in an atom of carbon, sodium, or iron. The same is true for neutrons and electrons. So what gives an element and its distinctive properties? What makes carbon so different from sodium or iron? The answer is the unique element or quantity of protons each contains. Carbon, by definition, is an element whose atoms contain 6 protons. No other element has exactly 6 protons in its atoms. Moreover, all atoms of carbon, whether found in your liver or in a lump of coal, contain 6 protons. Thus, the atomic number, which is the number of protons in the nucleus of the atom, identifies the element. Because an atom usually has the same number of electrons as protons, the atomic number identifies the usual number of electrons as well. In their most common form, most elements also contain the same number of neutrons as protons. The most common form of carbon, for example, has 6 neutrons as well as 6 protons, for a total of 12 subatomic particles in its nucleus. An element's mass number is the sum of the number of protons and neutrons on its nucleus. So the most common form of carbon's mass number is 12. Carbon is a relatively light element. Uranium, in contrast, has a mass number of 238 and is referred to as a heavy metal. Its atomic number is 92, but it contains 146 neutrons. Um, it has the most mass of all the naturally occurring elements. The periodic table of the elements shown in Figure 2.4 is a chart identifying the 92 elements found in nature, as well as several larger unstable elements discovered experimentally. The elements are arranged in order of their atomic number, with hydrogen and helium at the top of the table, and the more massive elements below. The periodic table is a useful device because for each element, it identifies the chemical symbol, the atomic number, and the mass number, while organizing elements according to their propensity to react with other elements. The number of protons and electrons in an element are equal. The number of protons and neutrons may be equal for some elements, but are not equal for all. That one's set. Isotopes. Although each element has a unique number of protons, it can exist as different isotopes. An isotope is one of the different forms of an element distinguished from one another by a different number of neutrons. The standard isotope of carbon is carbon-12, commonly called carbon-12. C12 has 6 protons and 6 neutrons for a mass number of 12. All the isotopes of carbon have the same number of protons, therefore C13 has 7 neutrons and C14 has 8. The different isotopes of an element can also be indicated with the mass number hyphenated. Hydrogen has 3 common isotopes, shown in Figure 2.5. An isotope that contains more than the usual number of neutrons is referred to as a heavy isotope. An example is C14. Heavy isotopes tend to be unstable, and unstable isotopes are radioactive. A radioactive isotope is an isotope whose nucleus readily decays, giving off subatomic particles and electromagnetic energy. Different radioactive isotopes differ. A radioactive isotope is an isotope whose nucleus readily decays, giving off subatomic particles and electromagnetic energy. Different radioactive isotopes differ in their half-life, the time it takes for half of any size sample of an isotope to decay. For example, the half-life of tritium, a radioisotope of hydrogen, is about 12 years, indicating it takes 12 years for half of the tritium nuclei in a sample to decay. Excessive exposure to radioactive isotopes can damage human cells and even cause cancer and birth defects. But when exposure is controlled, some radioisotopes can be useful in medicine. For more information, see the career connections. No. The behavior of electrons. In the human body, atoms do not exist as independent entities. Rather, they are constantly reacting with other atoms to form and break down more complex substances. To fully understand anatomy and physiology, we must grasp how atoms participate in such reactions. Key is understanding the behavior of electrons. Although electrons do not follow rigid orbits a set distance away from the atom's nucleus, they do tend to stay within certain regions of space called electron shells. An electron shell is a layer of electrons that encircle the nucleus at a distinct energy level. The atoms of the elements found in the human body have from 1 to 5 electron shells, and all electron shells hold 8 electrons except the first shell, which can only hold 2. This configuration of electron shells is the same for all atoms. The precise number of shells depends on the number of electrons in the atom. Hydrogen and helium have just 1 and 2 electrons, respectively. If you take a look at the periodic table of the elements, you will notice that hydrogen and helium are placed alone on either sides of the top row. They are the only elements that have 1 electron shell. A second shell is necessary to hold the electrons in all elements larger than hydrogen and helium. Lithium, whose atomic number is 3, has 3 electrons. 2 of these fill the first electron shell, and the third spills over into a second shell. The second electron shell can accumulate as many as 8 electrons. Carbon, with its 6 electrons, entirely fills its first shell and half fills its second. With 10 electrons, neon entirely fills its 2 electron shells. Again, look at the periodic table. It reveals that all the elements in the second row from lithium to neon have just 2 electron shells. Atoms with more than 10 electrons require more than 2 shells. These elements occupy the third and subsequent rows of the periodic table. The factor that most strongly governs the tendency of an atom to participate in chemical reactions is the number of electrons in its valence shell. A valence shell is an atom's outermost electron shell. If the valence shell is full, the atom is stable, meaning its electrons are unlikely to be pulled away from the nucleus by the electrical charge of other atoms. If the valence shell is not full, the atom is reactive, meaning it will tend to react with other atoms in ways that making the valence shell full. Consider hydrogen, which its 1 electron, only half filling its valence shell. This single electron is likely to be drawn into relationships with the atoms of other elements so that hydrogen's single valence shell can be stabilized. All atoms are most stable when there are exactly 8 electrons in their valence shell. This principle is referred to as the octet rule, and it states that an atom will give up, gain, or share electrons with another atom so that it ends up with 8 electrons in its own valence shell. For example, hydrogen with 6 electrons in its valence shell is likely to react with other atoms in a way that results in the addition of 2 electrons to oxygen's valence shell, bringing the number to 8. When 2 atoms when 2 hydrogen atoms each share their single electron with oxygen, the covalent bonds are formed, resulting in a molecule of water. In nature, atoms of one element tend to join with atoms of another element. Fuck. Damn it. Oh, in nature, atoms of one element tend to join with atoms of another element in characteristic ways. For example, carbon commonly fills its valence shell by linking up with four atoms of hydrogen. In doing so, the 2 elements form the simplest of organic molecules, methane, which also is one of the most abundant and stable carbon-containing compounds on Earth. As stated above, another example is water. Oxygen needs 2 electrons to fill its valence shell. It commonly interacts with 2 atoms of hydrogen, forming H2O. Incidentally, the name hydrogen reflects its contribution to water. A hydrogen is the water maker. 2.2 Chemical bonds. Learning objectives. By the end of this section, you'll be able to explain the relationship between molecules and compounds, distinguish between ions, cations, and anions, identify the key difference between ionic and covalent bonds, distinguish between nonpolar and polar covalent bonds, Alright. See if I get in there. Right at the end of this section, you'll be able to explain the relationship between molecules and compounds, distinguish between ions. Oh, I said that already. Distinguish between nonpolar and polar covalent bonds, explain how water molecules link via hydrogen bonds. Atoms separated by a great distance cannot link. Rather, they must come close enough for the electrons in their valence shells to interact. But do atoms ever actually touch one another? Most physicists would say no, because the negatively charged electrons in their valence shells repel one another. No force within the human body or anywhere in the natural world is strong enough to overcome this electrical repulsion. So when you read about atoms linking together or colliding, bear in mind that the atoms are not merging in a physical sense. Instead, atoms link by forming a new chemical bond. A bond is a weak or a strong electrical attraction that hold atoms in the same vicinity. The new grouping is typically more stable. I can't do this, I'm sorry. I'm so tired.